Hi there. Welcome to the talk. I'm presenting why are visually grounded language models, VLMs, bad at image classification for NeurIPS 2024. VLMs represent a family of models designed to learn a joint distribution of image and text tokens, typically through an autoregressive approach. They generally include a vision encoder paired with a language model and a connecting projector. VLMs have shown impressive versatility, excelling in tasks like image captioning, visual question answering, visual reasoning, and even more advanced agent-based applications. In this study, we revisit the fundamental task of image classification using VLMs. To use a VLM for image classification, we simply ask the model about the content of an image, choose from candidate classes, and check whether its response includes the correct class name. Surprisingly, we found that VLMs like GPT-4v or Gemini perform significantly worse than CLIP on standard benchmarks such as ImageNet and Flowers. This raised a big question. Why is this happening? We rigorously investigated this question through a series of hypotheses, each carefully tested. Our first hypothesis focused on prompt variation. We wondered if poor prompt design might be the issue, so we experimented with a variety of prompts, including more advanced chain-of-thought prompts. The results showed that prompt variation had very limited impact, indicating that prompts alone weren't the problem. The second hypothesis addressed label space size. We thought perhaps having too many classes in classification benchmarks, like the 1,000 classes in ImageNet, might be a limiting factor. We tested this by reducing the number of classes. When reducing from 100 to just 2 classes, we saw the gap between LLaVE and CLIP narrow slightly, but it still persisted, even in binary classification. Our third hypothesis examined the inference method. Asking the VLM to generate exact class names might be too challenging, as it might produce synonyms. We adjusted our approach to measure the probability of each class name. We used the probability inference technique to select the highest probability of all the class names. While this probability-based approach improved accuracy, the gap between LLaVE and CLIP remained. The fourth hypothesis was about information loss. CLIP's encoder fully encodes information for classification, but it's unclear if information degrades as it propagates through multiple LLM layers. We checked this by training a probing network on the final VLM layer to assess information retention. Surprisingly, we found that most information was preserved, but it couldn't be effectively decoded. The fifth hypothesis was on the training objective. Traditional classification uses cross-entropy loss, while VLMs use a text generation objective, which might be suboptimal for classification tasks. To test this, we converted classification datasets to an instructional format and fine-tuned the VLM using a text generation objective. Surprisingly, fine-tuning closed the gap, boosting LLaVE's accuracy on ImageNet to 86%. Our final hypothesis focused on data. We theorized that VLMs hadn't seen enough classification-specific data or classes during training. We analyzed the distribution of training data and its influence on performance. We discovered a strong linear correlation between the frequency of a class in VLM training data and the VLM's accuracy on that class. Combined with our fine-tuning results, we concluded that data matters significantly. Through these hypotheses, we highlight a data-centric view of VLM training, showing that adding multimodal data is essential for aligning VLM performance and that performance increases linearly with added data. Finally, why use VLMs for classification when CLIP already performs well? We believe that classification forms the foundation for more complex capabilities. For instance, identifying whether a mushroom is poisonous requires first identifying its species, a task that VLMs, like Gemini, currently struggle with. Therefore, improving classification capabilities in VLMs is essential, as it forms a solid foundation for more advanced functions, such as knowledge utilization and reasoning. To further test this, we created ImageWiki QA. Using Wikipedia pages for ImageNet classes, we generated multiple-choice questions with GPT, masking class names, and replacing them with ImageNet images. To answer these questions, models first need to classify the ImageNet object correctly before leveraging knowledge to answer. Current VLMs struggle with classification, leading to poor performance on this benchmark. However, when we fine-tuned LLaVE on the ImageNet classification dataset, we saw substantial improvements in classification ability which also enhanced its general capabilities, improving ImageWiki QA performance by 11.8%. Here are our key takeaways. Thank you for watching, and please check out our paper for more details.